Now we are going to gain some intuition about elliptic curves. Especially we are going to understand them in an algebraic way. In the sense how we are going to define the operations on the elliptic curve points. So first of all, what is an elliptic curve? In general, an elliptic curve is an equation of this form: y square is equal to x cubed plus ax plus b, where a and b could be some arbitrary numbers of a field. Okay, so now you see a graph. So this is a graph of real number fields, right? So here we have like the decimals, everything is allowed here. We will be working with modular prime fields, right? But this is the general equation. The equation that is chosen in SCCP 256K1 is slightly different. Okay, it's in a much more simplified way. It will be y square is equal to x cube plus 7. So this is the equation used in SCCP 256K1. Now we want to work with the points in the elliptic curve, right? The points in the elliptic curve. There are various points that satisfy this equation, and that points form the curve, and we can think about set of all points in the elliptic curve. Now we need to form a group. Remember, a group is a mathematical abstract mathematical structure which has some nice properties. One of the properties is if we take any 2 points in that group and you operate them. So a group is a set plus a binary operator, and you operate them, the third element should also be an element of the set itself. So that property is called closure. And then we need the property of identity element, inverse, and associative property. Okay, so these 4 properties are necessary. And the property of the group is also important for defining the discrete log problem. All right. Now let's think about it. Okay. So given a point, we need to add 2 points, right? So we need to add the same point. We need to define this addition of 2 same points, addition of 2 different points, and what is the identity element? For this elliptic curve, we are going to assume that the identity element is a point at infinity, meaning that point cannot be plotted in the graph, right? So it's kind of like an abstract concept. What is infinity as a number? Infinity as a number is the largest number which is bigger than any possible integer or real number or whatever. Okay, it's like an abstract concept. So how do we, at least, but in groups, we need to be able to reach the identity element. Okay, we can simply define that the infinity will be the identity element, and we can say that any point plus infinity is equal to same point. This definition is possible, but how do you reach the infinity element? Because we need to find A inverse such that A plus A inverse should give the infinity. Right? We need to be able to find them. Okay. So the way that we are going to define the operation on this elliptic curve should satisfy all these properties. We cannot simply add the x coordinates and the y coordinates, or we cannot simply come up with random formula, because that the result of the random formula may not be a point in the elliptic curve. So we need to give a mathematical structure to the operations that we are going to perform. I'm going to use the tools here, right? So let's say this is a point A. As you can see, it intersects with, if I draw a line through a point A in the graph, it intersects with at most 3 points, maximum 3 points. Okay, so in this case, wait a minute. In this case, it meets with exactly 3 points. And you should be able to verify that it won't meet the curve at more than 3 points. It will meet the curve at exactly 3 points. right? That is because of the property of this elliptic curve equation. Because in the left hand side we have y square, in the right hand side we have x cube. You can kind of like ignore the plus 7 for this like argument. And if you only consider the positive side, right, the positive y-axis value, that x cube will always be an increasing function, and it has this kind of the structure, like this structure, and this makes sure that if you draw a line through any point in the curve, it meets the curve at exactly 3 points. I mean, the argument that I'm giving is not precisely mathematical, but with this graph, you can kind of like convince yourself. Okay, you can actually mathematically prove this rigorously by yourself. Maybe that's an exercise for you. Now we define the point A plus B as not exactly C dash, but C this point D. Okay, so we compute A plus B in this way. So this D, this will be A plus B. So if I draw a line through any 2 points, it intersects the curve at the third point, and I basically reflect the curve. Okay, what is the relationship between C and D? If C is x3 comma y3, then D will be x3 comma negative y3. It's just y value is simply negated, right, reflected over the x-axis. Okay, so this is the case of A and B, where A and B have different x values. So here the x value is like it's approximate, it's near -2. For B, the x value is 0 point something. Okay, but what happens when you try to add 2 points in the elliptic curve with the same x value? Right. I mean, you can just take the screenshot of this. I'm going to erase the contents of this board. All right, and yeah, let me just remove them. So now we are going to talk about the addition of 2 different points with the same x coordinate value. Let's draw a line like exactly perpendicular to the x-axis. So now A and B, both of them has the same x-axis value. Now the points, now you notice that this line, it never interacts with this curve at any point, right? So it meets the curve at exactly 2 points. In order to define the addition, we need 3 points. Okay, so we say that this line intersects the curve at the third point at infinity. Okay, so infinity the identity point. So basically A inverse, if A is equal to x minus y according to our elliptic curve, the addition operation that we have defined, A inverse is simply x minus negative y, so that we get to the point at infinity, which is the identity element that we have defined here. You can programmatically encode it very simply. The identity point simply has, right, both x and y axis value as 0. There are like different ways to encode that programmatically, so like you don't have to worry about that so much. So this is how you reach to the identity element, and this is how you find the inverse, like pretty straightforward. All right. But what about this A plus A, the doubling of a point? You can think of that A plus A. Let me just remove these things. As a tangent. Okay. Now, yeah. So this is a tangent to A. At the curve. A tangent is a line which just touches the curve at exactly 1 point. At this point, right? So at this point, so this does not touches the curve. So this tangent it just grazes over the curve. Okay. And as you can see, the tangent, it probably meets the curve at this point. This may not be exactly accurate, but you can get the idea. So now this B is not A plus A. But if you simply invert it, so this C will be A plus A. Okay, so this C will be 2a, which is a plus a. This is how you find the doubling of a point. So these are all the different cases or to think about elliptic curve point additions. And of course, this point is also quite tricky. I mean, this point is not quite tricky. Adding this point with this point is straightforward. You just draw a line through it. It meets at the third point and draw a perpendicular line and you find the addition. But what about this line? Which is always interesting. Again, okay, the tangent to this point is interestingly point at infinity, right? Because the tangent to this point, it never meets the curve at any other point, right? Yeah. I hope this gave you the intuition about understanding the elliptic curve operations. And this graph and this visualization works only for real numbers. But we know that in our SACP256K1 cryptographic implementation, we are going to be work with integer modulo over a prime. That field, we are not going to plot the curve over real numbers. We are going to plot the curve over some integers with respect to modular operation. And we have already saw that curve is not going to be predictable and smooth like this. It will be all over the place. You won't be able to draw any patterns over that. And that is one of the very important property of the cryptography. You don't want others without the private key to make any sense of that information, right? So, and that adds to the difficulty of the discrete log problem as well. Okay. In the next video, we will learn how to derive these points in a formula, in a mathematical formula, so that the mathematical formula could be encoded in a computer program to find the addition of the points using your favorite programming language.